Hello and welcome to the lecture Generative Vision Models. In this lecture, we are going to cover the generative modeling for computer vision. Then we discuss the different vision models and we conclude our lecture by describing some application of generative models in computer vision. In this part of the lecture, we start understanding how a generative modeling or a generative model can be used for computer vision. That is the major aspect of this course. So, as we have understood already, that generative modeling is basically a branch of machine learning, and that can be wide range of application in computer vision. That basically focus learning the underlying distribution of visual data, like images, video, 3D scene, etc., so that they can create a new realistic samples. Now, as we know that our simple computer vision or image processing task with specifically recognizing and classifying image, these generative models learns how images formed and can create, construct and modify. So it generating a new but realistic samples. This may be images, video, 3D, volumetric things. So we also know a generative model learns probability distribution P of x of data where x represents image or other vectors. So that first we have to concentrate what kind of computer vision task a generative model is used for. It generates new image, synthesize a synthetic data. What it can be used? It fill in missing image regions, popularly known as image inpainting. It can enhance image resolution. That means super resolution. It convert images from one style to another. It's called style transfer. It create the synthetic training data because somewhere this we can understand. For supervised deep learning models require a huge number of training data set, and these data set not always very easily available. It is costly and time consuming to create. So in this case, we can really easily create a large volume of synthetic training data. It also can generate videos and 3D objects. So there, understand, there is a wide range of application of generative modeling in computer vision. So in this part of this lecture, what we are trying to understand, basically we just for as a definition level, what are the different vision models that we used. We start with variational autoencoders, popularly known as VAEs, generative adversarial networks, autoregressive model, diffusion model, normalizing force, and so on. So one by one, we try to understand what are these models and what are the jobs or what are the tasks computer vision these particular models can do. Now, a variational autoencoder is a type of generative neural network that learns a compressed continuous representation of data and can generate new samples similar to training data. Now, what this statement means? Now, first of all, we know about autoencoder from our previous machine learning lectures. Autoencoder means which reconstruct the input. But unlike a standard autoencoder, which in general maps an input to a single point to the latent space. What does this mean? That if we see in autoencoder, it compresses the input to a latent space where it has a set of points. That's why which maps the input to a single point in latent space. The variation of an encoder maps an input to a probability distribution as latent distribution. Typically, it's a Gaussian distribution. See here. And when we elaborate in the later part of this course, we can understand what exactly that means. Variation autoencoder uses encoder-decoder architecture with variational inference to model data distribution. So we have to understand what is variation inference is to model distribution, allowing for tasks like image synthesis, denoising, and anomaly detection. Now let us try to understand a very simplistic what is normal autoencoder and what is the basic difference between normal autoencoder and variation. Now you can see here the image is there. Autoencoder means is encoder and decoder. It generally reconstructs, but it may not reconstruct exactly. There is a noise, so it's a reconstruction noise. Now this is encoder, this is decoder. This is basically a kind of compression. Important thing is this. Now this latent space consists of some values. So it's some data points. So this in case of normal autoencoder, latent space is the values. On the other hand, a variation autoencoder can see this latent space is basically a set of distributions. Like it's very homogeneous, may not be that much homogeneous. But in nature it's definitely a Gaussian. So in spite of values, it creates a set of homogeneous, non-homogeneous distribution of Gaussian distribution, for example. Now this encoder is set of distribution. What this decoder do? It takes some point from the distribution. One important thing it is that the output may not be same as it not reconstruct the input. Rather, from the distribution, actually what the distribution is? Distribution is a kind of a attributes that dictates this object or an image, and some point that is chosen from these attributes and creates this image. That essentially a new image that is not part of this input training set, and that's why it's become generative model. But normal autoencoder is not a generative model, just reconstruct. So that is the basic understanding. Variation of autoencoder in comparison with normal. Now, what are the major vision tasks that is basically done seeing this variation autoencoder? Variation autoencoder generates new images, video, etc. It can easily run meaningful latent representation. It performs interpolation between image samples. Also, it can be used for image compression and anomaly detection. Next, we'll see another generative model. It's a very popular model. Its name is Generative Adversarial Network, popularly known as GANs. So this generative adversarial network is a deep learning model that learns to create a realistic synthetic data, such as image, video, audio, text, by training two neural networks in competition with each other. So it consists of two basic parts or two neural networks. One is called generator that creates fake data or generate the data from the random noise. It tries to produce the output that looks like a real image. Whereas a discriminator, this is also a neural network that receives both real and generated data and tries to distinguish between. And these two neural networks are competing to each other to converge such a way that a image that looks very realistic can be generated. Let's see. So first of all, start with generator. A generator can be thought of as a skilled forger whose objective is to create a synthetic data that is indistinguishable from them. So what we'll see in this figure that this generator is basically a kind of neural net that take input from latent variable, let's say Gaussian noise, and try to generate scripts. So this is basically generated. For the time being, we'll say that it's a fake data. And what is the basic purpose or goal of the generator? It creates this kind of images that is looks like it's very actual real world data. Okay. Now come back here. So it begins with a random input vector, as we said, that is the z vector, it's the latent vector z Gaussian noise, which typically sample from a simple probability distribution such as distribution. Now this vector serves as a latent representation. This encoding abstract feature that guides the generation process. The generator then transforms this noise vector into a synthetic sound, we observe, such an image. Now, an intuitive analogy is that an artist starting with a random scribble and gradually refining them conventional. So, kind of this thing. Through training, the generator learns to map points in a latent space to realistic data sample, with the ultimate goal to producing outputs that are realistic enough to fool the discriminator into classifying them as legitimate. So, basic understanding, what we have understood from the figure, the goal of generator is to generate such a sample which may be generated. We can say it's a fake, it's not real, but it looks like. Okay, let's try to understand what is discriminator. Discriminator is another neural network, and it viewed as a skill detector whose role is to distinguish between authentic data and synthetic data produced. So what it's trying to do, it's trying to distinguish between the generated data, by the time it's the fake data, and actual real world. So it receives data samples as input, either a real example from the training data or a fake sample generated by generator. And outputs the probability score, Tx, represent the likelihood that the sample is generated. Now you can see here, what is the role of discriminator? Discriminator is basically a kind of classifier that take that from two inputs, from real data and its generated of data, and try to find out is the real data or. And this loss is called adversarial loss. This loss is basically backpropagate both discriminator as yeah, so that it be trained. These two are trained separately. When discriminator is training or being trained, generator is used. When generator is being trained, discriminator is used. And in this way. Now say that a value close to 1 indicates that discriminator believes the sample is real, while a value close to 0 suggests that it's right. That means it is just a discrimination between try to discriminate. So an intuitive analogy is that an expert examining a painting and determining whether it's the original masterpiece or and carefully crafted portrait. So in throughout training process, discriminator continuously improves its ability to detect subtle difference between real and providing feedback that the generator produces interestingly in increasingly realistic samples. So one thing is very important to understand here, that both the neural network are basically improving by this loss function. This discriminator is improving in that way. It can more effectively, accurately distinguish between fake data and real data. Whereas the generator is trained on improving such a way, can generate fake data or generate such data which can, when this learning is going, alternative learning is going, at the end of the day, we find that discriminator cannot able to discriminate between real data and when we can find that good or very the data which is very close to the real data. Now, why generative adversarial is good for generation? The GAN is particularly effective for image generation because of the way they are trained. Instead of trying to reconstruct every pixel exactly, they learn to produce an image that looks realistic to a discriminated network. So this adversarial training, you can say using adversarial, is generator's goals to fool discriminator into believing generated images are real. And discriminator learns feature that distinguishes real images. So this is a kind of competition between them. The generator learns to match those features. This pushes the generator to create realistic texture, edges, lightning, and fine details. And it produces sharp images. Right? Many traditional generative models, being early, very short encoders, optimize pixel by pixel reconstruction. For a reconstruction of such images, the model often averages multiple possible outputs, okay? Blurred images. But can avoid directly minimizing pixel. Instead, optimize the perceptual realism, which typically results in sharper images. So, GAN perform for generating more realistic images. What are the other advantages? It can learn the complex data distribution very well. Images have highly complex distributions of objects, shapes, color, texture, facial relationships. It can be very much easily understood or easily modeled by GAN. GANs can learn these patterns without explicitly modeling probabilities, allowing them to generate elastic samples of high dimensional spaces. So it generates high frequency data. It can excel at generating fair standards, hinge texture, fur, grass, fine edges very well. These details are often difficult for reconstructionist models to reproduce. And this continuous latency. GAN maps the latent vector Z to an image nearby latent vectors tend to generate similar images, enabling image interpolation, attribute manipulation, trials. For example, moving through latent space can gradually change its spatial expression, age, hair color. Our next model is our autoregressive generative. What do you mean by autoregressive? An autoregressive generative model is a type of machine learning model that creates data sequentially by predicting each new element based on the elements that came before it. And that's why it's called. The term autoregressive refers to the model's ability to use its own previous outputs as inputs for generating the subsequent. Rather than producing an entire sequence simultaneously, the model generates data one step at a time, making each prediction dependent on the preceding. Okay, so there is different autoregressive models. This approach is widely used in applications such as NLP, image generation, audio synthesis, time series forecasting, by maintaining coherence and capture sequential patterns. Mathematically, what we say that this is a joint probability and it can be explained or described in this way. So the model learns conditional probabilities of system. Okay. So what are the different autoregressive models? First of all, pixel RNN is one of the earliest autoregressive image generation model. Salon generates image pixel using recurrent neural networks. It captures spatial dependencies but computationally expensive due to its sequential nature. Then come the pixels here. It replace the recurrent neural network with masked convolution layers, enabling faster training while still generating images from pixels. All these models will come in details later part of this lecture. Various of such pixels in class further improves image quality and training step. Then come the transformer, and for this vision application, vision transformer. This model applies to the transformer architecture to image generation by creating images in sequence of pixels or image batches. The major thing is self-attention, which is one of the important mechanism in transformer. So this self-attention mechanism allows it to model long-range dependency more effectively than CNN-based approach. More recent autoregressive models that VQ, VAU plus transform. The vector quantized variation autoencoder compress image into discrete attributes. This is autoregressive transform. Then models and generate these codes, producing high quality images with reduced computational cost. Some examples, DALI is one important model which transforms autoregressive architecture to generate image from text descriptor. It models image sequence to discrete visual tokens and predicts them sequentially based on input text and previously generated tokens. So these are some examples of this. The party is that large-scale progressive transformer developed to text. So it generates image tokens sequentially and demonstrates strong capabilities in producing detailed and coherent images from complex text blocks. So these are very recent models. So basically, autoregressive model is transformed. As we can see, there is a two part. One is encoder part and decoder. There is a multi-head attention, basically the self-attention, and then feed-forward network, and there is some sort of skip connection with LNR. That before that, there is the input embedding and position. in this decoder part also, that is output and positional. After that, masked multi-area attribution and some similar add normalization, and there is a multi-area attribution, and there is some feed forwarding on it. These are the standard transformer. You will see details what actually it produces. This is also important autoregressive models. One of the major thing models is diffusion models. What diffusion models? Is a class of generative machine learning models that create new data such as image, audio, or video by learning a reverse gradual noise process. That is very interesting. What do you mean by reverse gradual? So there is a two parts. Is the forward pass and backward pass. During training, random noise is progressively added until it becomes nearly pure noise. And then the model then learns how to remove this noise step by step, reconstructing the audio. So this is learning step. When generating new content, the process starts with a random noise and iteratively denoise it to produce the first output. So this diffusion must become highly influential in AI because they can generate high quality and diverse results. In power systems such as image generation tools, making them a key technology in modern building. Now, there is a two process as we discussed. In forward process, we keep on generating noise so that it will completely noise. And then in reverse process, we successively denoising it. So, in forward process, gradually add Gaussian noise data over many time steps until, and backward process, that the noise is gradually removed by sampling using analytics and so on, so that it appears out. So diffusion models explicitly encode this process using the concept of forward and backward. So this is as a whole the diffusion process. Our final generative model, normalizing Prof. This is a family of generative models that learns complex data distribution by applying a sequence of invertible and differentiable transformations, the simple probability distribution, such as Gaussian distribution. What it is basically do this x row of x, that is the Latin representation, and do the inverse process with that x. Each transformation gradually maps a simple Latin variable into a data sample that resembles the training data while preserving the ability to compute exact probability densities through the change of variance. Because every transformation reversible, since both efficient data generation and exact likelihood estimation, making them attractive tasks as image generation, density estimation, anomaly detection, representation learning, and so on. The main advantage lies in combining tractable probabilistic modeling with flexible neural network-based transformations, enabling the modeling the high complex distributions. So this is the row-based generative models, minimizing the negative time. So this is the. So what are the different applications in computer vision? As we see that these models, image synthesis, generate realistic human faces, landscape, artwork, and objects. Image to image translation, like sketch to photo translation, day to night, domain adaptation, some are this kind of transformation or translation. Superlusion will increase the image quality and resolution. Medical imaging, satellite imaging, so on. Then image in painting, field machine visions in image. Data augmentation generate the synthetic training samples from limited data. video generation, realistic videos from the text prompt libraries, and 3D generate 3D objects, the neural radiance scales, virtual models. These are the typical applications. So in this chat, we basically touch upon generative modeling of computer vision, generative vision models, and application in computer vision. The next part, we start the mathematical applications, which is essential to understand the generative AI computer vision. Thank you very much.